let's talk about how the normal distribution, normal stress distribution on this section dx. So let's talk about the devices, and we learn the normal stress distribution. You just say very simple here, distribution. So with the normal stress distribution, we already learned that when you have a bending moment, then it creates the normal stress, and how that look like. Let's review that one here with that differential slide. I redraw that section dx, and of course we have the load wx, and then just only the normal stress, so it due to the moment. So for here I only draw the moment, something like we did in a poor bending in lesson 8. So m plus em, and with that we have again this e dx and neutral axis na. So as you already know, for the distribution of the normal stress, let me draw it down a little bit further so that we can solve the distribution of the normal stress. M plus dm m plus dm. So that's the normal stress that we have here. For the normal stress distribution, it will be 0 in the neutral axis, and it will be maximum at the outermost fiber, if you recall that. M y over I. Remember that? Go to the bending lesson that you can have that. So with that, we can draw the normal stress. It's 0 at the neutral axis, and with that moment, positive moment, it will create tension at the bottom, and that is the distribution of the moment in the bottom. And then similarly on the other side we also have the same, and it in tension, and 0 at the neutral axis. And then it will also 0 at the neutral axis on the top, but it will be in compression and get maximum at the outermost fiber. So in compression with that moment. So the beam, it contracts on top and expand at the bottom to create that normal stress distribution. So this so far nothing new. And from that, how can we have the free body diagram for the lower section? And that is, we draw the free body diagram of lower section. What are the lower section that I want to looking at here? So let's cut this member. Let's cut this member out here, and I consider this portion either lower section. This lower section. So one portion, the lower section of the differential slide. If you look at the book, they cut the top with that lower section, and it 2dx. And let me call the y is the distance from the neutral axis to the location that I cut. Is that location. Okay, so that is the Y that I'm called from the neutral axis to the position that I want to cut. That is Y. So what do I have? Let's draw the free body diagram for the lower section. Free body diagram for the lower section, and now I put in 3D. So that is the lower section that we have it in here. Okay, so with that, let's put it in 3D of that section. So we have, and this is a little bit abstract, so you look at carefully in here. So I have that portion and put it in 3D. So that portion here. Okay. So we can have the hidden line for that portion. So only that green portion that I wrote down, and as you can see with that 3D, I have that the dx up there for the 3D. It become the dx this position, and we have the width of that one is basically, as you can see, the portion, if we draw it down here, that is the cut that I want to cut down, and that is the position that I want to consider. So look at the other side. This distance is T, the thickness of the member, from the cross section that you see there. So from that, let's draw the how the stress and load distributed on this member. On the left side, as you can see, you will have the normal stress portion, this portion, right? And then you have normal stress of this portion. And let me delete that, but remind you that what you have to go to right on the left hand side and right hand side. So let's draw that out here for normal stress that I just showed you, and on the other side smaller and get bigger at the end. So you have that. That normal stress, and we have here, for the top one and for the bottom one for the normal stress. It look busy. Let's try it again. So what here that I do, so the normal stress, the top is the outermost fiber, that what you have. At the cut we have a smaller stress, the black line that you have here. So it's not uniform, as you can see from the bending moment, and so it create that. This is top, this is bottom, so you have that one as well. So that is the normal stress distributed on the left hand side, and that I call this is a sigma left hand side. And similarly on the other side, on this portion, I also have the sigma right hand side. So it's the same at the outermost fiber, the get maximum at the cut, the black portion here. So let me draw that black portion so we can easy to know this is where we stand on here with different color that you have there. So from that one, we have the normal stress on the right hand side at the cut and at the that normal stress at the right hand side. just make a few representatives so it will not look busy. So that one, we call that either sigma, the normal stress on the right hand side. And then with that, sum up on the sigma at the right hand side and on the sigma at the left hand side, on the sigma at the left hand side, it creates a force. And that force, I call that either force in the left hand side, that I call the total force due to the sigma left hand side that we have is total, that we call force at the left hand side. And similarly, on the other side, I also have the sum up on the stress become the force. I call it force in the right hand side. And as we cut in the black surface that you have it in there, right? You cut at a position y from the neutral axis. Then what we have in here, we have the shear stress on the cut, remember, and on that cut here, on that black surface that I cut, as you can see, it will have an equivalent shear, and I call that shear V horizontal, on the surface that I cut here, that y from the neutral axis, because you cut, will expose the shear stress to make the body in equilibrium. Okay, so with that here, I call that sum up on the shear stress on that surface become a sum VH, sum up on the force of that. So keep in mind what you have here, the force in the left hand side is not the same as force in the right hand side. They are not the same. Why? Because the moment on the left hand side is m, on the right hand side m plus dm, and assume they have the same cross section. So from that, as you can see, if I sum up on the force, in x direction equal to 0. So what do I have? I will have sum up on the force in x. You will have the force to the left hand side, plus VH. So that is sum up all the force go to the left. It had to be equal to, for equilibrium, all the force go to the right, so it's right hand side. Everyone see that? That's the equation to make the body in equilibrium. So with that, the concept, we draw that one, and because very abstract in that draw, so keep that, look and watch out carefully how I make the lower section and why we have the force in left hand side and right hand side, and the shear force due to the cut at y from the neutral axis. So next we go to the math to determine how the shear stress distributed throughout this cross section.